So to kick us off, it'd be great to have you guys introduce yourselves, kind of yourselves and your company, and where you fit into the next generation landscape.
My name is Jing Nealis, the CFO of SES AI Corporation. SES AI is a leading company in developing lithium metal battery, the next generation battery technology for EV applications, as well as UAM, urban air mobility. We currently work with Hyundai, GM, and Honda to go through the qualification process, A, B, C sample, to try to commercialize our technology by mid-decade. So if you kind of look at the future of battery we kind of grew from lead acid to lithium ion, and what's next? So we believe lithium metal is next, the big step change for battery technology, and so as our OEM partners. We are in A sample stage. We have been in A sample stage since 2021. We're going to transition into B sample by the end of the year. And then C sample maybe in 2025 to commercialize. So a lot of exciting things going on. And also worth mentioning is we do have AI in our name. One of our pillars in our technology is AI, which we've been working on for the last 6 years to build the algorithm in our battery to gather data from the materials of the battery, the manufacturing process, the usage data to predict the health and recycling value and a lot of things in the battery itself through the life of the battery. Also using AI for material science discoveries. So,
thank you very much, Srini.
Sure, thank you. Thank you for having me on the panel. LI Metal is a company that is trying to vertically integrate and develop a value chain for lithium metal production using a chloride-free process. So we are looking at directly taking lithium carbonate to lithium metal, but are also working to develop a vapor deposition process for scaling up really thin foils. Anywhere between 2 to 20 micron is what we're trying to do. Like Jing was mentioning, we are working with about 27 customers who are all in today A or B sample stages. And given their scale up, we are working to scale our capacity to supply anodes to them with our first commercial PVD machine, which should be able to supply anywhere, depending on the thickness of the foil that they want, 300 to 500 megawatt of anode capability by middle of next year. And then we are working with multiple clients around the globe to really get to about 4 to 5 gigawatts of manufacturing capability for their C sample testing sometime in 25 or early 26.
Perfect. Emily?
I'm Emily Bodwin, the CEO and founder of Pure Lithium Corporation. We're a Boston-based company. My co-founder is Professor Donald Sadoway from MIT. And we are just 22 years old. We're a company of people. And what we do is make lithium metal electrodes for our own batteries. So we differentiate ourselves by, first, we electrodeposit lithium metal from brines. Thank you. We electrodeposit lithium metal from dilute sources of brines, therefore unlocking unconventional sources of lithium. So think about a concentrate produced by a company like E3 Lithium in Canada. We electrodeposit our lithium metal onto a piece of copper, so you have an actual battery component in one step, and we do this very cheaply, inexpensively, and quickly. So our first granted patent is literally for the vertical integration of lithium metal in a battery manufacturing facility and a battery. The reason for this is lithium metal is very reactive. It's very difficult to ship. And it's very important that the quality of the metal is perfect or the battery's not going to work very well. So we feel at Pure Lithium it's very important to develop localized supply chains from the ground up. We're not interested in making a battery with unobtainium. We pair our lithium metal with vanadium, which is the fourth most abundant transition metal in the Earth's crust. It's not used in the lithium ion industry today, and it's a perfect host to accommodate the vast capacity of lithium metal anodes. So that's a little bit about our company, and learn more as the panel goes on.
Okay, thank you very much. You touched on something really important there, that lithium metal itself is is really quite highly reactive. So one of the things I wanted to ask the panel in general is that traditionally it's been said that lithium metal has failed due to its reactivity with electrolytes. What has changed over the past few years that means lithium metal could be successful in next generation battery chemistry? So if we start with Emily, and we'll work our way back down.
Sure, absolutely. So first, solid state is not synonymous with lithium metal at all. There's been a lot of electrolyte innovation. SES is a very good example. So the flammable electrolyte in your lithium ion battery and your lithium metal battery is the same. It's an organic. Lithium ion batteries are just as flammable because the electrolyte is what is incredibly flammable. So by replacing the electrolyte with something non-flammable, you can have a very safe metal battery that incredibly well. And a lot of innovation in this space with highly concentrated salts and solvents, like SES has done, and other pathways.
From our viewpoint, is spot on, right? It's the electrolyte is the key difference that's happened. The industry quickly jumped from carbonate-based solvents to all solid state, and then they forgot about what incremental innovation, right? Like Emily was mentioning, you don't need to go all solid state to be successful and safe. What a few innovators over the past couple of years have shown is you could have, you call it whatever, right? A different solvent, whether you call it liquid, polymeric, whatever you want, whatever name you want to give it, it's not all solid state, and they are very much compatible with metal anodes. The previous generation, kind of when you had the carbonates, they were quite reactive with the carbonate solvent. The carbonate solvent was flammable, you had dendrite formation, and it just led to a series of failures. And now with the tweak in the electrolyte system, plus the know-how on the anode production that's coming through in terms of cost or ability to produce, when you marry those two, you basically have a battery system that is successful in the market now. And you see that being scaled up pretty quickly, especially over the last 6 months. You're seeing people quickly talking about going from A samples to C samples in the next 12, 18 months, which was not the case, right? So I think the electrolyte innovation is the key.
Yeah, exactly. So I think one, lithium metal is not new, right? Our company started 11 years ago out of basement lab of MIT, actually Professor Satterway's lab in MIT, and has been working on lithium metal since, and it was not even new back then. But the challenge for lithium metal is the traditional electrolyte would not prevent the dendrite to grow. So the dendrite is a needle structure. When it grows, it pokes through the separator and shorting and safety issues. So our technology in SES, one of the core that we have is in the electrolyte. Basically, it's not solid. It's more of a hybrid. It's liquid, but the traditional liquid electrolyte is more like a cup of water with some salt in it. It's very liquid, and it's flammable. It's not safe. It's used actually in all of our EVs today in the lithium-ion batteries. But our electrolyte is high concentration solvent and salt. Think of it as another way around is a bucket of salt with a couple drops of solvent that coordinate with the salt. And it completely changed the way dendrite grows. It's no longer a dendrite. It becomes mossy lithium, more like a Healy structure that is not pointy. So it just changed the way it grows so it could be safe, right? One of the major issues for lithium metal to commercialize is safety and then dendrite. So as the other two panelists said, that really the core is material science and electrolyte and changing the way dendrite grows. Of course, the anode is another core material, and lithium metal being the lightest metal on the periodic table and kind of change the whole, increase the density and much lighter and all the other benefits. But the core to make lithium metal work is in the dendrite, is in the electrolyte.
One point that you said triggered for me on the material innovation, what's changed also on the anode is the ability to put in SEIs on top of the anode and able to see those, right? The SEMs and other analytical tools have come so long in the past few years that we are actually able to visualize now how a certain type of SEI and how that reacts with the electrolyte system or protects the electrolyte system and prevents dendrite formation. So I think overall, the material innovation over the last decade is what has really driven this ability to now accelerate on next generation anodes.
Yeah, definitely. So I think the panel's touched on a really important point there, that anode innovation and battery innovation isn't specific to just developing an anode chemistry. In order to enable a novel anode or a novel cathode, you need to develop across the cell and understand how each of your components is degrading and interacting with one another. So we discussed kind of lithium metal batteries and where they could be. What do you see as the biggest bottleneck towards the commercialization of lithium metal batteries today? Emily, do you want to kick us off?
Sure, absolutely. And the actual quality of the lithium metal, to me, is the biggest bottleneck, and it's actually why I started the company named Pure Lithium. If you have a perfect film of lithium that is, within half of a micron of tolerance, that means smoothness across the surface, and you don't have valleys and voids in the material, and you don't have other non-conductive impurities that cause side reactions, you have even current distribution, and you don't have dendritic forming. So in my view, it's a few things. The system has to work as a whole. The electrolyte is, super the battery work, but you also have a huge advantage in life and performance if you start with a fresh, beautiful piece of lithium.
From my view, the previous panel here said something very interesting, right? In the end, it is about the economics. It is about delivering quality, but at the lowest cost that you can. For next generation batteries to be adopted, you need to compete with graphite. You need to be at cost parity to lithium-ion batteries, right? You can start off as being expensive at the initial stages, but you have to show the industry a pathway to really drive those costs down. If you are not able to really scale, and if you're not able to get to those parity costs, you will fail. Part of this is also that investment that is required, right? They said invest quick and invest fast. And right now, most of the investment is coming from venture capital or private investors and not from the OEMs, right? They need to recognize that the industry needs this capacity. It will not be built up overnight, right? I mean, we have seen the kind of delays. It takes 5 to 7 years to build something right now. So if your projection there, right, even if 10% of that goes to next generation battery technology, you have 400 gigawatts of capacity required. We don't have metal. The entire world doesn't have enough metal, right? Today, if you take all of the metal, you don't have capacity anywhere close to that, right? So a lot of capacity has to be built up. The industry needs to realize that they have to work together and then drive those investment. And you will need substantial skin in the game from OEMs to do this. Small innovators can only take this to a certain level, right? Beyond that point, it's the funding that comes into the industry. So cost focus, quality focus, and then funding. Those are the three constraints. And then discipline to drive the project, right? To make sure everything is on cost and it's delivered on time.
Sure. Do you have anything to add?
I agree with both of them. Just to add, I think two things. One is the technology has to work. At SES, we've proven the technology is working back in from 2025 to 2021 through the pre-A sample, right? And then the second stage is can you make it big enough? Instead of this little tiny cell, you have to make it this large. That's for a car, like a Hummer EV would take 300 of those large 100 amp hour cells that we're making today. And then make it fast enough and with high yield and all of that. And let me tell you, making battery is very difficult. But that's on us to work with OEM to prove that safety. And then given it's a new technology, new chemistry, the process to go through to test the boundary conditions is tremendous amount of work to go through that process with OEM partners to feel confident it's safe, the performance is good, and then you can still make it and scale it up. So those are the things we're working on us to do. But The second thing is like on the supply chain side, when the technology does work, right, where the thin lithium foil come from, that's where Emily and Sri's company will come in play, where there will be a group of companies in the next gen batteries to kind of help this to grow. We will need to be able to make thin lithium foil on copper cost effectively with a good machine and everything. So there are different ways to make it and a lot of innovation happening. So I think all of these kind of have to play out for us to be a very large scale and compete with lithium ion.
Yeah, I think the panelists again have raised a really important point here that in order to be successful on a mass market scale, you have to hit a whole load of different performance metrics. One of them being cost competitive. In early stages, you can be successful in luxury markets by having a very high quality product. But in order to really breach that mass market commercialization and commercial scale, you need to be able to compete on that cost front. So with that in mind, as we look towards the future anode space overall, there's a whole load of different innovations that are being explored, silicon-based, anode-free as it's called, silicon oxide. Where do you see these technologies fitting in with lithium metal? Do you find them to be competitive, or do you think they're complementary to the energy transition? Jing, if we could start with you this time.
First of all, there's no such thing called anode-free. Right? I'm not a scientist. I'm a CFO, so there has to be anode. But anyway, so I think there are different technologies, silicon, lithium metal. This is not in my opinion, winner take all. The market is gigantic. There are space for different technologies. There's space even for lithium metal if there are different approach to lithium metal. Having said that, there are challenges for each technology. Silicon is easy to make low percentage silicon battery, but if you're like very high percentage silicon, I think it's even harder than commercializing lithium metal. But it's good to have different routes and possibilities to kind of broaden the path. It's a big market for a lot of people.
Sure. Look, from our viewpoint, we are agnostic. We think there is a need for all the technologies, all of the above. One thing that we are very clear and within our organization that we say is all roads will lead to lithium metal, because even if you have silicon graphite, you need to pre-lithiate that to avoid first cycle losses. So all of them, doesn't matter what the next generation technology is, will need a source of metal and will need a form or ability to put that metal onto the anode, whether it onto a current collector, right? Whether it is pure lithium metal anodes, those anodes free, which are actually 3 micron or thinner lithium deposits. They're not just a current collector, right? Whether you go to that technology, whether you go to silicon graphite, all of them will need some form of lithium deposited on them. And so you need a source of lithium and you need deposition techniques, whether that's electrodeposition, vapor deposition. We'll have to see how that plays out in the industry. But you need lithium metal and you need deposition capability. And mix doesn't matter, right? It's so huge that mix of whether what dominates and whether lithium metal anodes are small will not matter. When you have 4 terawatt of battery capacity being built out, even a small niche market is a large enough market for most players.
So I'm a little bit more bullish on lithium metal is something that will place lithium ion batteries, much like the vacuum tube and the transistor in the semiconductor industry. And this is, in large part because if you, going to your earlier slide, Roy, you did a great job. Graphite, 372 milliamp hours a gram. Lithium metal, 3,860. 1 lithium per 6 carbons. Okay, this just doesn't make a lot of sense. It's 40-year-old technology. It's brilliant. We recently filed a joint patent with Stan Whittingham, who invented both the lithium metal battery and the lithium ion battery. But he invented the lithium metal battery first in 1977 at Exxon. So we always knew that was the holy grail. And silicon expands by 400% when you put lithium into it. So there aren't a lot of choices when you take a good hard look at the periodic table. We also have issues that lithium metal can solve. Jing was pointing out how these large format cells, you'll need 300 of them. That's a lot better than 7,500. There are so many spillover benefits of using lithium metal. Cooling, for example, there's so many cost savings at large scale that it makes a lot of sense to use lithium differently. Use it on the anode side of the battery, don't use it on the cathode, and you can have a battery that's under $50 a kilowatt hour. But we need to really combat climate change, because to your earlier point, Rory, nobody is going to buy a battery that costs more than lithium ion. They're not going to do it. These things have to get cheaper and cheaper and cheaper, or forget about climate change completely.
Yeah, so that kind of links into the understanding of that kind of commercial timeline, and knowing that these emerging technologies, as any technology does, needs time to develop and optimize. The panel have touched a few times on that formal automotive qualification procedure in different stages, first being A sample, moving through to D sample, which is product delivery. So I just wanted to ask the panel what their opinion is of the commercialization timeline for lithium metal batteries. It's something that is often touted and timelines are given, but what do we think is a realistic timeline to see the first lithium metal batteries in a commercial application? So Srini, if you could answer that.
Look, where are we with our customers? Like I said, most of them are in C samples in 25, 26, right? That's what they're targeting. And then maybe D samples closer to 29, 30 kind of a time frame is what guidance that we are getting. So commercialization towards the end of this decade, everyone is trying to accelerate. It would be great if they accelerate, but if there's acceleration, then there is difficulty and challenges with the supply chain that need to be resolved as well. So it's not always you accelerate and it's easy. There are other challenges that you'll have to deal with, but definitely you will see C samples in 25, 26 for solid state batteries. And depending on how successful they are, maybe D samples before the end of the decade.
And Emily, does this align with what you believe?
I mean, we're waiting, right? We're waiting to see. But Chichao SES has been the leader in the space for a long time. So, I mean, really, I'm going to throw the question at Jane. When are you guys going to make it to market? Because that's the answer I'm going to roll with.
Our goal is to commercialize by mid-decade, so 2025, 2026. So the OEMs we work with is ABC. There's no D. So once we get to C, it's pretty much it. We're transitioning to B this year. B will take probably a year. A is the hardest. It takes 3 years. And B 1 year, then C. C is really the last step where the OEM tests the entire car with the battery in it in different conditions, the pack, the BMS and everything, the windshield wipers, the tires and the whole thing. So by the time to C is pretty much locked in. So really it's A and B that's critical. Our goal is to get to commercialization by mid-decade.
And with that commercialization, would you see that as mass market commercialization or entry to the market with national scale?
It's hard to say. I think probably at initial stage, we're talking about single-digit gigawatt hours, but it's really kind of a ramping process, right? Start with something that's single-digit gigawatt hour, and then kind of ramp from there. Yeah.
Perfect, yeah. Really good answer. It kind of pitches the idea of next generation battery technology still taking some time to come through. I think that's a natural part of companies progressing through the formal automotive qualification procedure, which naturally takes time, and there may be delays along that pathway. But it's really interesting to hear that all three panelists believe before 2030 we should see lithium metal batteries, and SES believes that by 2025 we should see them entering the first commercial applications. So one of the discussions that surrounds lithium metal batteries is understanding that with excess lithium metal foil comes increased lithium intensity. I wanted to ask the panelists what their opinion is on increased lithium intensity, whether lithium metal batteries will naturally have that, and how that might affect the market and demand going forward. If we can start with Emily.
Sure. So we're aiming for a zero excess lithium battery. We want a stoichiometrically correct cell design. And when you have this, we don't see volumetric expansion that is very typical when you just slap a lithium foil in there and pair it with some lithiated cathode like NMC. So we're aiming for less lithium intensity, and even less because we're not putting any lithium on the cathode side. So we only want to put in the battery what we're actually going to use, and this just keeps costs down. Why add active material to a battery that you're actually not going to cycle?
We don't see it today. We do see a lithium intensity increase from all the clients. We're working with about 30 different customers. From our viewpoint, the intensity will go up until they optimize the battery, right? Today, whether you do add 3 micron to 20 micron thickness, depending on how thick they want, they have the same cathode. They're not changing the lithium out of the cathode. So it is added lithium going into the cell. They're trying to balance it. They're trying to make sure there's not too much of an excess inventory of lithium. But it would be great if they get to that, right? If they get to a point where there's no excess lithium and they have the right amount of lithium and that's sufficient, based on the samples, large quantities we're supplying people today, nobody's there yet, right? It would be perfect if they were, but unfortunately, in the short term at least, I think you will see the intensity go up. You will need more lithium, not less. And then plus the electrolyte itself are changing as well. So that will add a little bit more lithium intensity. So it might eventually go down, but initially I see it spike up before it starts to come back and then go down.
Yeah, I agree. We're at about 20 microns. So I think, initially probably, it's the other panelists said, I agree. And over time, it's a balance, right? You reduce the density, but then the electrolyte has to work. And then we're also testing different cathode materials, LFP, NMC, and there's even newer cathode technologies that combining MFP and different things to see where the boundaries are and how everything works out. But right now we're still at like 20-ish.
So we've had a couple of questions through on the tablet, and I'll summarize them all together. They're broadly working towards kind of pricing here. And so there's a weird price dynamic with lithium metal foils at the moment through traditional mechanisms where as the foil gets thinner, the price of the lithium metal foil gets more expensive. Could I just ask the panelists to kind of describe why that is and where novel lithium metal deposition techniques might enable that price sensitivity to come down slightly? So I'll start with Emily, if that's okay.
Sure, absolutely. So for our technology, it's completely the opposite. When we're making lithium metal, we're electrodepositing it onto a piece of copper. So what happens is we're growing it from this piece of copper upward. So when we want to stop and make the film, say 5 microns, we just turn the electricity off. That's it. We don't have to, work. It actually costs us more to make a thicker film because it's a little bit more electricity in the process. So it's actually quite the opposite. What has been really, really hard for lithium metal researchers and anyone in this room, has anyone in here ever built a lithium metal battery before? Okay, you don't feel our pain. It's painful. It's really painful. And when you get a, extruded foil that you've spent, $3,500 on, right? And it's coated in mineral oil and you can't even get the oil off of the thing before you put it in the battery. And it's got more impurities in it. Maybe it's 80% lithium, but you found nitrogen, you found boron, and you find all this stuff in there that is just going to go haywire in your battery. It's really, really, really difficult. So it's a challenge. We don't need the thick extruded foil. And until we get a method to just, really quickly, inexpensively put it on the copper, we're not going to see this battery come to market. And who's going to pay for it? These are just some of the big challenges. And when we're talking about lithium intensity, when we have LFP, for example, it's a great cathode material. It's a workhorse. It's amazing. It's, 80% of the cost of it is lithium. So we're going to take lithium metal, which is expensive, and we're going to pair it with something that contains lithium in it. Of course, the lithium intensity is going to go up, but that's not the correct way to think about it. We need to think about not being afraid to look at other cathodes and innovate. The only reason we use lithiated cathodes now is because they're optimized for your lithium ion battery manufacturing. And it's just been copy paste and copy paste. Graphite is not any kind of active material. It's just a host. It's a little sponge for the lithium to sit. So we really need to not be afraid to think about other cathode chemistries. If we're going to talk about using less lithium, why put it on both sides?
From a cost point of view, right, why industry costs are high is because most of the foil that you get is rolled. extruded, and then rolled. As you go thinner, it takes more time. You have to do it slow. Lithium, as you know, the thinner you get, it rips. Any imperfection that you have in the ingot that they use in terms of air bubbles or air pockets or any nitrides or oxides that are formed will rip the foil. So there's a lot of scrap. The scrap rate is 30+% as you go really thin. All that cost comes back to the foil, right? And that's what you're paying for today when you do extrusion. Like Emily said, if you do bottom up, whether it's electrodeposition or vapor deposition, your costs are more cost competitive. But as we have scaled up, one of the challenges that you replace, right? You replace the lithium metal cost with the cost of the throughput. Today, the market needs really small quantities of samples. They're all in kilowatt scales at best. And people are asking for 100 meters, 200 meters of samples to do their testing. When you have a machine, like the commercial machine that we are building today, which can make 2 million meters square, and you're taking few 100 meters for development, the cost of that machine is going to make the foil expensive. The beauty of this is when you do vapor deposition or other, where you build from scratch, when you scale, and we fill that 2 million meter squares of that machine, your cost is going to be extremely cost competitive. We are working, today, if you look at it, foils go for about $90 a meter square. The target we have received from the industry and we are working towards is to get that down to $3 to $5 a meter square, right? At scale, at multi-gigawatt scale, and that is the pathway. So you have 2 orders of magnitude cost reduction that needs to happen. Part of it is scale, part of it is optimizing the scrap, part of it is the substrate. Copper is expensive, copper foil is expensive. Part of it is what do you do with the substrate? So it's not a single impact on cost. You have to work with your battery producer to make sure whatever you're doing works for them. Look, it's great if you have a process that makes ultra pure lithium, right? In reality, the industrial process, unfortunately, we don't have it today, right? The technology today gets you 99.9, and maybe you do have impurities, mainly calcium in there that our process eliminates, but then you have to start with really pure raw materials. So I think there is a lot of development to happen, a lot of innovation is already happening around the space to really drive the purity and quality, but also the cost. So don't go by today's cost is my only advice, is as the scales, the cost. Look, anybody who wants to look has to just go back and look at how lithium ion battery costs were, right? They were $6,000 plus a kilowatt hour if you go into the 1990s. And within a decade, they were in the $200, $300, and now $120, $130, of course, with the about $150 right now with the price bump that we have seen. But that drop happened because of scale, right? And that is what you need to get into this next generation batteries, and then the price will be competitive. So don't go by today's price on your modeling. Go with what is potentially possible in the future when you get scale.
Xing?
Yeah, definitely. Don't look at today's cost. When CATL commercialized EV battery with BMW, I think their initial cost was in the thousands of dollars per kilowatt hour. So I think, we work with vendors in this space to kind of help them, and they help us to be able to have the supply of thin lithium foil in large format. There are different ways doing it. Lamination is one way. That's like, we have vendors who are already doing that. And then of course there's a deposit or vibration and different ways to try to bring the cost down more and then make it more efficiently and everything. So for us, it is a bond material, and then we work with our vendors to test different vendors producing it different ways and see which one works better for our lithium metal battery, and also work with the vendor to scale up. Ultimately, the supply chain need to scale up in order for lithium metal to be in scale, right?
Perfect, great answers again. So we're coming towards the end of the time with our panel. I'd like to ask them one final question each. The next generation battery space and broadly the future anode space is one where there's lots of miscommunication and misunderstanding. So the question I'd like to pose to our panelists is if there's one thing you can clarify today, if there's one miscommunication that you can make clear, what would that be? And if we could start with Emily, that'd be great.
Absolutely. Lithium metal is not synonymous with solid state. And generally, batteries need liquid in them to help the lithium travel through the cathode. So until someone has somehow made lithium be able to just shuttle itself to the copper and out through the external circuit, you need liquid in your battery. Lithium metal will work with liquid. Don't think for a second that solid state is the future or the next generation of batteries. I'm not confident I'll see it happen in my lifetime.
The one thing that I would like to mention is, and that I hear is, there's enough lithium metal to service the industry. And I just want to make sure everyone understands there is not. In fact, there is so little lithium metal out there, and capacity, even announced capacity, is so small that you cannot service more than a few 100,000 vehicles with all the announced metal capacity. There is a lot of capacity required that has to be built out. New technologies are required, and I just hope people wake up, including the politicians, and really look at where that metal is going to come from. We are focused. The good thing is we are focused on the mining of the salts, but eventually we'll have to go further downstream in terms of differentiation. The good news is the industry is actually more Western focused, right? The next generation industry is so focused in North America and Europe that there is an opportunity for us to really get a technological advantage by focusing on supply of metal from localized mineral sources. And I think that's an advantage that people don't see, and we should leverage.
I will echo Emily. I've spent the last 3 years educating investors. Solid state is not the future. Lithium metal is the future. Solid state is the electrolyte, and that's not the technology to increase density, fast charging, and all the stuff. Lighter battery is in the lithium metal. So the buzzword of solid state, I think, is like people ask me, "Are you guys solid?" And no, we're not solid, but it doesn't really matter. The OEMs we work with don't really care, right? You just need to deliver the next generation lithium metal batteries, whether solid, liquid, hybrid, whatever way that make lithium metal work. Currently, solid state wouldn't work to start with, but it's a huge buzzword that everybody kind of just think solid state is the future, but really there's a lot of confusion, in my opinion.
So that's great. That's 3 great key messages to take home from the panel today, and I hope everyone enjoyed the panel as much as I did. If you could join me in giving a round of applause to the panel for their time today.